Okay, so welcome back. Physics 20. We are going to now move into circular motion and Newton's law, and we're going to be looking at circular speed and how we can relate or kind of go through terminology, and then we'll end up looking at how do we calculate centripetal acceleration, and then we'll go into some net forces, looking at centripetal force and how we keep things on the road and do roller coasters and whatnot. Okay, so some terminology. We have a cycle now. That's one complete back and forth or oscillation. So if you think of a pendulum, if I have a pendulum hanging on this string, one cycle would be there and then back. So anytime I get back to my original starting point, that would be considered one oscillation or one cycle. A revolution is one complete cycle for an object moving in a circular pathway. So just think about a revolution. You turn around once. So if you go around the clock, if the hands of the clock go around the clock once, that's one revolution around the clock. A period, and now a period, the symbol for this is a capital T. And this is the time required for an object to make one oscillation. And so the unit that we use is a hertz. So a hertz, oh, sorry, I'm on the wrong side. So we're looking at a cycle, a second per cycle. So it's kind of a weird way of thinking about it. How long does it take to take one cycle or one revolution? Frequency now, this is the one that uses hertz as its unit. This is the number of cycles per second. So when we look at frequency, we are looking at a hertz. So we look at 1 hertz is equivalent to 1 cycle over seconds, or your number of cycles per second. Okay. Sorry, so let's put number of cycles per second. Or sometimes you may see written as s to the -1. An RPM is a revolution per minute, and this is your cycles per minute. So how many cycles do you get in 1 minute? So there are 2 formulas that we can use. We can use period, which is equal to 1 over the frequency, and we can use frequency as being 1 over the period. And so this is just, if you think about the units, right? If you look here, a period is a cycle, a second per cycle. And then on this one, it is a cycle per second. So when we want to convert between RPMs and frequency, if we are going from frequency to RPMs, we are going to take a look at this. So frequency, the unit is a hertz. We are going to not multiply it, sorry. A hertz is also a cycle per second. We are then going to change it to RPM. So RPMs, remember, are cycles per minute. So we want to multiply 60 seconds for every minute. So that would give us cycles per minute. So the seconds cancel and we're left with cycles per minute. And this is equal to an RPM. So you don't have to write that out every time. It's just to show you that if you want to go from frequency to RPMs, you always multiply frequency by 60. Okay. If we want to go in the opposite now, if we want to go from RPMs to frequency, we look at the opposite here. So 1 RPM is equal to 1 cycle per minute. Now if I multiply to get cycles per second, because that's what a frequency is, I have 1 minute for every 60 seconds. Minutes will cancel, and I will now be left with cycles per second. So if you want to go in the opposite direction, you're just going to divide by 60. So if you want kind of an easy way to remember it, if you just write down here, frequency to RPMs, multiply by 60, and if we go in the reverse, RPMs to frequency, we're going to divide by 60. Okay, let's try an example. Example number 1. The hard drive in the figure below stores data on a thin magnetic platter that spins at a high speed. The platter makes one complete revolution in 0.00833 seconds. Determine the frequency in hertz and RPMs. So, they're telling you that you make one revolution in 0.0083 seconds. So, I am telling you how long it takes to make one cycle. So how many seconds for one cycle? What value is this? Or what quantity is this? If you said period, you are correct. 0.00833 seconds per cycle. Okay, they want us to solve for frequency, and they want it in hertz and in RPMs. So, if I want to solve for frequency, the formula is 1 over the period. So if I take my frequency and I go 1 over 0.00833, you will get 120 hertz. Okay, because this is now a cycle per second. Because these are our seconds down here, right? So if I want to get RPMs now, I'm going to take my 120 hertz and I'm going to multiply by 60, and that will give it to me in RPMs. So 7,200 RPMs. So in case we have to switch between those units, that's how you would move between them. Normally we're going to be using frequency or period. We won't usually see a lot of RPMs in our equations. Okay, so let's relate period and frequency of circular motion. So to determine the speed of an object that's moving in a circular pathway, we can just use the average speed equation. So we can go v circular is equal to the change in the distance over the change in the time. In circular motion, if you travel around a circle, so if I start here and I move in a circular pathway, what is that equivalent to in relation to the circle? That would be its circumference. Capital C. So, our change in distance on a circular pathway is equal to the circumference. The equation for circumference, 2 pi r. So now I can take 2 pi r, which is equivalent to the distance around a circle, and I can plug it in here. Okay, so this can now become 2 pi r. And the time that it takes to make one revolution, so time for one revolution, we just talked about that. That would be our period, which is a capital T. So the change in time now becomes the period. How long does it take to make one revolution? So now I can take my period, which is now equal to delta T, and I can plug it in here. And this now becomes 2 pi r over T. So this equation, VC equals 2 pi r, and r is the radius, divided by T, this is on the data sheet. So you do not have to derive it. You do not have to memorize it. This equation is given to you. And again, we can manipulate it to solve any one of those properties. Okay, so a pebble is stuck in the treads of a tire at a distance of 36 centimeters from the axle. It takes 40 seconds for the wheel to make one revolution. What is the speed of the pebble at any instant? So first, let's write down what we know. So the pebble is stuck in the treads of a tire at a distance of 36 centimeters from the axle. So the axle is right here in the center, so they are giving us the radius. So radius is equal to 36.0 centimeters. The time it takes to make one revolution is a period, and that is 0.40 seconds, we need to solve for the circular speed. Formula for circular speed is on the data sheet, so you don't have to memorize it. 2 pi r over t. We plug it in, 2 pi, and they don't ask for specific units, so we can just keep it as centimeters and end up with a centimeter per second value. If they wanted us to convert to meters and they wanted an answer in meters per second, we could then convert centimeters to meters. But they don't ask it, so we don't need to do it. So it's going to be 2 pi times 36 all over the period, 0.4. If you plug that into your calculator, the circular speed will be 5.654 meters per second. And then if we look at significant digits, I've got 3, I've got 2, so we're going to round it to 2. VC will equal 5.7 meters per second. And that would be our final answer. So we're going to pause the video here for a few minutes, and I'd like you to do practice problems on page 250, numbers 1 to 3, and page 251, numbers 1 to 2. Okay, so we're back from that break. If you would like to take a look at a closer look at centripetal acceleration, you can definitely read page 252 and take some notes on how tires are designed. Not mandatory, an optional kind of information bit that you can read there. Okay, so let's move on to now and look at how what factors will affect the magnitude of centripetal acceleration and centripetal force. So how fast you're spinning or your rotational speed is one factor, but what are the other factors that will affect it? So using similar triangles, and you can see how they do this on page 253, they have derived the following equations. So centripetal acceleration is equal to your circular speed squared all over r. If you recall from the last set of notes, our centripetal speed is 2 pi r over t. So what I can do now is I can plug in this 2 pi r divided by t into my equation for centripetal acceleration. So this now will become 2 pi r over t squared divided by r. If I bring that exponent into the bracket, it'll become 2 to the power of 2, which is 4, pi squared r squared all over r times t squared. So take a second to let that sink in. And then we can simplify the r's. So now the r on the bottom will cancel, and I'm left with 1 r on top. So our new equation for centripetal acceleration is 4 pi squared times r over t squared. These two equations, or actually all three of these equations, are on your data sheet. So you do not have to derive them. So this guy, and this one are on your data sheet. Okay. We can, though, take a look at mass now. So remember, the radius will affect our centripetal acceleration. Mass does not. It's not in the equation for centripetal acceleration, but it will affect our centripetal force. So remember, when we look at F net, we can determine the F net by taking the mass of the object and multiplying it by its acceleration. Remember, Fc, or centripetal acceleration, is just like a net force. It's all of those center-seeking forces. So it will also be equal to the mass of whatever object we're looking at and the centripetal acceleration of that object. So we can take this equation and we can add into it our equation from the data sheet on centripetal acceleration, and we can plug it in right here. So now we can get a new equation, Fc equals the mass times 4 pi squared times r all over t squared. And then if we just simplify it, make it look a little nicer, it would be 4 pi squared times your mass times your r over t squared. I mean, you don't have to simplify it that way, but it just kind of looks nicer. So this equation, unfortunately, is not on the data sheet. Okay, so this equation is not on the data sheet. So you must derive it. So anytime you have a question, you need to remember that you can take this formula for centripetal acceleration, and technically, really, you could take this formula too, and you can plug them both in for this AC. Okay, and again, remember, the ones that are in brackets or in squares, those are red squares, those are the ones that you're going to find on your data sheet. Okay, so let's try a couple of examples, and then I'll let you guys have some time to work on some practice problems, and then we'll come back and we'll just kind of go back and forth between doing some examples and giving you some time to work on practice problems. Okay, so let's write down what we know for this next problem. A DVD, example number 3, has a diameter of 12 centimeters and a rotational period of 0.1 seconds. Determine the centripetal acceleration at the outer edge of this disk. So, they have told us that the diameter is 12.0 centimeters, and the period is equivalent to 0.10, and actually here, let me write this a little higher. The period is 100 seconds. They want us to solve for centripetal acceleration. And if we take a look at the centripetal acceleration problem or equations, we could look at centripetal speed or circular speed up here and our radius, but we don't have centripetal speed, so that's not going to work, circular speed. Or we could look here, 4 pi squared times r over t squared. Well, I have my r, or I could get my r, and I have my t, so that equation would probably work best. So 4 pi squared times my r over t squared. Okay, so now I need to look at my diameter and I need a radius. So if I want to solve for my radius, it is going to be my diameter divided by 2, which will give me 12 over 2, which will give me 6 centimeters. We normally do our distances in meters, so we want to put it in meters because we need a meters per second for acceleration, especially if we're going to be using it in a force equation, right? So acceleration always has to be in meters per second squared. So if I take my 60 centimeters in 1 meter, there's 100 centimeters, so that's going to give me 0.06 meters. I can now plug in the information. So 4 pi squared times my r, 0.06, all divided by 0.1 seconds, and I'm going to square it. Don't forget to square it. Take a second, plug that into your calculator. So 4 pi squared times 0.06 over 0.1 squared, and we get a value of 236.87, and the units will be meters per second squared. Okay, significant digits, I've got 3 of each, so now my centripetal acceleration is going to be 237 meters per second squared, and that would be our final answer. Okay, I'm going to give you the practice problems, but we're not going to stop just yet. So if you want some practice problems like example number 3, you're going to take a look at on page 255, and you're going to answer 1 to 3. Okay, and we'll give you a second to do that in a moment. Okay, example number 4 now. Determine the magnitude of the centripetal force exerted by the rim of a dragster's wheel on a 45 kilogram tire. The tire has a radius of 4.80 meters and is rotating at a speed of 30 meters per second. So let's start by writing down what we know. So we have a mass of 45.0 kilograms. we have a radius of 0.480 meters, and we have a centripetal or a circular speed of 30.0 meters per second. They want us to calculate the magnitude of the centripetal force. So FC is our question mark. Okay, centripetal force is just like a net force. So I can calculate the net force or the centripetal force by taking the mass, and now I'm going to multiply by centripetal acceleration. I do not know the centripetal acceleration, but I've got a couple formulas for it. And if I look at what I have, I've got my circular speed. So my equation for centripetal acceleration, which is circular speed squared over r, would work. Because I have my r, I have my mass, and I have my circular speed. So now I'm going to take this version of centripetal acceleration and plug it in for the AC. So now it becomes mass times circular speed squared, all divided by r. So my formula now, so if I take a look, mass is in kilograms, which is what we want. Speed is in meters per second, and my radius is in meters. So now I just have to plug everything in. So this is going to become 45 times 30 squared all over 0.48. So if you plug that into your calculator, you're going to get 84,375 newtons. And then again, rounding to our proper digits, I've got 3, 3, and 3 here. So our centripetal acceleration, I've got too many digits, so I'm going to put it into scientific notation. 1, 2, 3, 4. It's going to be 8.44 times 10 to the 5 newtons. And they just wanted magnitude, so I don't need to say to the center. So your second set of practice problems are found on page 256, and you're going to do numbers 1 to 2. So we'll pause the video here, and then when we come back, we will keep looking at a horizontal system in circular motion. Okay, so we're back now. So now we're going to take a look at what's happening when an object is turning a corner. So moving in a horizontal plane, but we're going to make that circular motion. So it's easy to think of a car turning a corner and what's happening to that car. So when a vehicle goes around a curve, it is going to experience a centripetal force. And that centripetal force is going to be to the center of the curve. Okay, the centripetal force that is going to keep you on the road is going to be your frictional force. Okay, that's what's going to keep us on the road, is the frictional force. So when we have a car that's turning, or anything turning a corner, our centripetal force is going to be our frictional force. Okay, so let's write that over here. Our FC, centripetal force, will be equal to the force of friction. And we now remember from our dynamics unit that we just finished, what is the formula for frictional force? Hopefully it's still fresh in your mind. That is the coefficient of friction times the normal force of the object. So if a car takes a corner too quickly, the friction cannot hold the car in place, and therefore the car will skid off the road and go into the ditch. Okay, so that just means, i.e., the reason why you're flying off like that is that the force of friction cannot exert the needed centripetal force because remember, the centripetal force is going to be the static friction. And the car will slide off the road tangentially. Okay, so that's why you have to be more mindful when you're driving in the wintertime and turning corners, is because you're going to have less friction because we now have snow and ice, which is going to give us less friction between the wheels and the road, and you're more likely to continue sliding in a straight line. Okay, just a little note. Remember that kinetic friction is going to be present when the car slides with its wheels locked. Static friction is when no skidding occurs. So we want to get our maximum static friction so we're not sliding off the road. Okay, so let's take a look at question number 5. Determine the maximum speed at which a 1,500 kilogram car can round a curve that has a radius of 40 meters. If the coefficient of static friction between the tires and the road is 0.60. Okay, so for this one, I'm going to write down what we know. I have a mass of 1,500 kilograms. I have a radius of 40.0 meters. And I have a coefficient of friction of 0.60. We want to solve for the maximum speed. So we want our V max, which is really a centripetal speed, or sorry, a circular speed, when our centripetal force is equivalent to the static force of friction, right? Because we don't want the car to slide off the road. So because we're now dealing with static force or friction forces or frictional forces, we need to draw a free body diagram because we need to know what the normal force is going to be. So let's start off by drawing our free body diagram. Here's our car. Let's pretend he's turning to the right. So our frictional force will go in the right direction. Then if we're looking at the car in the Y, we will have a normal force from the road, and we will have the force of gravity pushing the car down. Okay, so we are looking for our maximum speed. So if we look in the X direction, our F net is going to be a centripetal force. And that centripetal force is all going to be due to static friction. We know the formula for static friction is the coefficient times the normal. We also know that our centripetal force is our mass times our centripetal acceleration. I am still trying to look for my speed max. So how am I going to get speed into my formula? So if we look at our centripetal acceleration, we know that AC is equal to centripetal speed squared all over r. So now I can plug that in for acceleration. So now this becomes mass times centripetal speed squared all over r will be equal to the coefficient times the f of n. If I want to now isolate for VC, or for our circular speed, I can multiply by r, divide by n on both sides. On the left side, mass and radius will cancel, so now I'm left with centripetal speed circular speed is equal to the coefficient times the normal force times my radius all over my mass. Then to get just circular speed, I'm going to square root both of these. Okay, so now we got to look at this and we have to say, well, wait a second. I don't know the normal. How am I going to solve for my normal force? So that's now where I'm going to take a look at my y. In my y, my F net is equal to, and let's say up is positive, Fn plus the negative f of g. And again, these F net statements are important, so you have to write them down. F net in the y is 0 because the car is not moving in the y direction. So now I know my Fn is equal to my f of g, and f of g is solved by m times g. So now Fn is equal to m times g. So now I can take this m times g and sub it into Fn. So here we go. So that's now going to be v circular speed is going to be equal to the square root of my coefficient of friction times my mass times my g times my r, all divided by mass. Can we simplify this again? We can divide out our mass. So now Vc is going to be equal to the square root of the coefficient of friction times gravity times r. Now we can solve. So centripetal speed is equal to the square root, plug in our numbers, 0.6, g is 9.81 unless otherwise stated, and r is 40. So if you plug that into your calculator and don't forget to square root it at the end, you will get a value of 15.344 meters per second, and it goes on. Again, looking at our coefficients of friction, I only have 2, so my answer is going to round to 15 meters per second. That's the maximum speed the car can go around the corner without sliding off or skidding off. Okay, so we're going to pause the video here, and I want you to try practice problem page 259, numbers 1 to 3. And we'll give you, I don't know, maybe 5-10 minutes, just depending on how much time we have here, to work on those. Okay, so let's take a look now at vertical systems in circular motion. So all the roller coasters that you've been on have been designed so that each car will have sufficient velocity to remain in contact with the track at the top of the loop. The speed of the car will determine the amount of centripetal force that you need to maintain the radius. So remember, my centripetal force is equal to m times the circular speed squared all over r. Okay, that's one of the equations we can derive. So we need to have a specific, whatever speed we're going around will determine how much force I need going through that circle to stay on the track. At the top of the track, we have 2 forces working in the same direction. So there's 2 forces that are acting as our centripetal force. This is at the top. So if you take a look at this picture here, what 2 forces are pulling on the roller coaster towards the center of the track? So we're going to say into the center is positive. We are going to have f of g, and the track is on a surface, so we will also have a normal force. So when we're at the top of the track, our centripetal forces will be the normal force plus the force due to gravity. Okay. When they are determining how fast to make the car go around the loop in order to maintain contact with the loop, they always want to look at the minimum speed that they would have to send you through. So they know that you have to reach that, at least that speed, in order to make it through the circular motion of the loop. So when they want to figure out the minimum speed that you need, they only look at gravitational force as being the centripetal force. Okay, so when we set the centripetal force equal to the force of gravity, we can determine the minimum speed. So when centripetal force equals the force of gravity, we can determine the minimum speed required to stay on the track. So we are looking at a free body diagram that would just have f of g going to the center. So you need to memorize, for a vertical system, FC, when FC equals FG, you can solve for your minimum speed. Okay, you need to memorize this, and it's for vertical systems. So think roller coasters. Okay, let's do an example, and then I can give you some practice problems, and then we'll come back and we'll talk about different scenarios when we look at those buckets or rolling around on a string. Okay, example 6. A 700 kilogram roller coaster car full of people goes around a vertical loop that has a diameter of 50 meters. What minimum speed must the roller coaster have at the top of the vertical loop to stay on track? So we should be paying attention to this minimum speed, and we're in a vertical loop. So first we know mass, 700.0 kilograms, right unit. The radius is 50.0 meters. Oh, sorry, the diameter is 50 meters. The radius is what we're going to want, is going to be 50 divided by 2, so that will be 25 meters. Okay, they want us to solve for V min, and when the circular speed is at its minimum, we know that Fc would have to equal Fg. The centripetal force will only be the force due to gravity. Okay, so we have a roller coaster on a track. The force due to gravity is the only force acting on it. We are going to say to the center is positive. We know the formula for mass due to, force due to gravity is m times g. We know that our F centripetal force is only going to be F of g. Centripetal force is also equal to mass times the acceleration, or centripetal acceleration, and the force of gravity is m times g. I'm still looking for this minimum speed, so I have to remember that centripetal acceleration is v squared over r. I'm then going to plug this guy in for my centripetal acceleration. So now this becomes mass times circular speed squared over r is equal to the mass times g. And now I'm going to isolate for my speed. So I'm going to divide by m. I'm going to multiply by r. M's cancel on the left and the right. My r's cancel on the left. So I'm left with my circular speed square is times the acceleration due to gravity times the radius. We are going to square root both sides. So now my circular speed will be the square root of acceleration due to gravity times the radius. Now we can plug it in. So this is now going to be 9.81 times 25. That is going to equal 15.66 meters per second. We are going to round to 3 digits. So the minimum speed that I need is going to be 15.7 meters per second. So that roller coaster has to be traveling 15.7 meters per second. Okay, let's pause the video. You're going to try practice problems page 262, numbers 1 to 2. Okay, so we are back again. Let's take a look at all the possible free body diagrams that we could have if we have an object moving in a vertical circle. So, for example, that cup of water that was on the end of a string, or just even a bucket of water going around a circle. So when we are at the top of the circle, so we're swinging around in a vertical pathway. When we're at the top, we have our string, and in the string, what force do we find in strings? Tension. And we also have the force due to gravity. So we would make to the center downwards positive. And if we had to write out our F net statement or centripetal force statement, it would be tension plus F of G. Okay, so the dash arrow is showing the direction of our velocity. Okay, if we take a look at now the bucket on its side, the only force acting to the center is now tension. The force of gravity is acting perpendicular, so the force of gravity is no longer a centripetal force. The only centripetal force we have is tension. And again, we always make to the center positive. So the force of gravity is not going to play any role in keeping the object in line with, or keeping it on that circular pathway. Okay, let's take a look at the bottom now of that swing, or that turning motion. Tension is still going to be going towards the center, so we're going to make to the center positive. But now the force of gravity is actually acting in the opposite direction. So now when I write my F net statement, or the centripetal force statement, it is going to be my tension plus the negative of my force of gravity. So it's very important, again, because we're dealing with centripetal force and it's a net force, we have to draw those free body diagrams so we know which forces are actually acting to the center and if there's any opposing forces. So when we are at the top and at the bottom, force of gravity is in our equation. When we are at the side, it is only tension because the force of gravity is now in the wrong direction. It's pointing downwards instead of to the center. Okay, so just a couple quick notes to recall. And then we'll do another example. I think we've got 2 examples left to go. Yeah, 2 examples. Well, 1 example, we'll do some practice and then some notes to go on. Okay, so recall. Centripetal force is a net force. So it is the net force of an object at any position. So it's the net force of an object moving in a circular path. Okay. Fc, the centripetal force, is determined, so if we look at those equations, so is determined by the object's mass, speed, and radius. Okay. Fg may contribute to centripetal force. So when you're in a vertical system, it'll be at the top and at the bottom of that circular motion. If you're on a horizontal, then it will never affect it because it's pulling down and you're moving in that horizontal plane. Okay, so Fg may contribute. So you have to draw that free body diagram to show which forces are acting towards the center or in the direction, in the plane that moves to the center. So Fg may contribute, may contribute to Fc, to the centripetal force. Okay, and remember, Fg will always be there, it just might not be in the plane or in the direction, or in, the direction of the centripetal force. Okay, let's try an example together, and then I'll give you some time to work on your own. A bucket of water with a mass of 1.5 kilograms is spun in a vertical circle on a rope. The radius of the circle is 0.75 meters, and the speed of the bucket is 3 meters. What is the tension on the rope at the bottom? Okay, first let's write down what we know. We have a mass of 1.5 kilograms. We have a radius of 0.5 meters. And we have a speed of the bucket that is 3.00 meters per second. And that's circular speed. So you'll notice that we kind of start to drop the little c there. But just remember, we're dealing with a circular motion. Okay, what is the tension in the rope at the bottom? So now I'm looking for my tension force. So they've told us it's at the bottom of the circular path. So we're going to draw our bucket. And then if it's at the bottom, the tension is going to the center, and the force due to gravity is acting in the opposite direction. So to the center is going to be positive. Remember, f of g can be determined by m times g. We're on Earth, so remember g equals 9.81. So let's start now by writing our F net statement. Okay, so, but again, circular motion, so it's going to be centripetal force is equal to the tension plus the negative force due to gravity. Don't forget, centripetal force is like a net force, so I can write mass times centripetal acceleration will be equal to T minus the force due to gravity. Now, when I take a look at my equation, I do not have centripetal acceleration as one of my values, but I do have speed. So, what equation do we know for centripetal acceleration that has speed in it? Yeah, centripetal acceleration is our speed squared over r. So now that's what I'm going to plug into it. So it's now going to be mass times v squared, all divided by r, is equal to my tension minus my force due to gravity. I haven't put in the m times g yet just because I want to manipulate the equation first. So now tension. I have to add force of gravity to both sides. So now it's going to be mass times v squared all over r plus the force of gravity. And then I can say mass times v squared all over r plus m times g. There's the formula for tension. So now I'm just going to plug in my values. Tension is going to equal the mass, 1.5 kilograms, times my speed, 3 squared, all divided by my r, 0.75, and then I'm going to add to it 1.5 times 9.81. So if you take a second and plug that into your calculator, so make sure you try the calculation. You are going to get 32.715 newtons. And we are going to 2 significant digits. So the tension is going to be 33 newtons. And usually we just want the magnitude. We're not going to ask you for direction because we know it's to the center of the circle. So normally we'll just ask for magnitudes. Okay, so we'll pause the video here. We're going to do practice problems on page 264, numbers 1 to 3. Give you about, I don't know, maybe 5 or 8 minutes, again, just depending on how much time is left in class. And then we're going to move on. Okay, we're back. So now we're going to try and relate frequency into our acceleration and centripetal force equations. So when an object rotates, the points on the object will move at different speeds. And this is true here on Earth because the Earth will rotate on its axis in 1 day or 24 hours. But if you're standing at the equator, you are going to travel a further circumference just because the Earth is wider there. When you're at point B near the poles, you are going to cover less distance in that rotation. So you are actually going to spin slower because everyone has to make the rotation or the cycle in 24 hours. Okay, so when you look at this graph, point A is going to spin faster, or when you look at this diagram, point A at the equator will spin faster because it has a greater distance to travel. So B/C, because it has a greater distance to travel in 24 hours. Point B is going to spin slower because we are going to spin again for 24 hours. Sorry, we're going to spin slower. Whoops. Because it has less distance to cover, or less distance to travel. Okay, in 24 hours. Whoops, in 24 hours. Okay, so the circular speed of A is going to be greater than the circular speed of B. Okay, so that means that we can use frequency to determine, we can use frequency and period to determine our centripetal force. So there's a couple things, formulas that we need to remember before we do these deriving. And these formulas too that we're going to derive are not on your data sheet. So you have to always be thinking about how can I plug in formulas I know into other formulas to get to a formula that's going to work for me. Okay, so these are some of the formulas we want to remember. We have centripetal force is equal to mass times centripetal acceleration. We know that centripetal acceleration could be speed squared over r. We also know that our circular speed can be 2 pi r over t. And we know the relationship between period and frequency. So t equals 1 over f. Okay, we are going to now try to take our our centripetal force, and we're going to try to get period into our equation. So let's take F of c is equal to the mass times the acceleration, centripetal acceleration. I am then going to plug in AC is v squared over r. And then I'm going to plug in for my v squared. I'm going to put in 2 pi r over t. And then if we simplify this, mass 4 pi squared times r squared all over r times mass. We can then simplify that to being, and this is the same equation that we had to derive before, right? 4 pi squared times r over t. So now we've put period into our formula. So again, these are formulas you're going to have to derive. They're not on the, oh, and I forgot my mass, sorry. Oh, because I completely messed up there. Let's go back, sorry. This mass should be a t squared, and that should be t squared, and then we should have a mass up here. Goodness, going too fast. So there's our derived equation. So I'll give you a second to make that correction. Okay, now if I want to take this derived equation, I can then add frequency to the equation. So I'm going to start over here with Fc is equal to 4 pi squared times m times r all over t squared. And then you're going to remember here, what is t equal to? 1 over f. So now I can plug in 1 over f for t. So now this is going to become 4 pi squared times m times r, all divided by 1 over f squared. If I bring the square across the bracket, and then if I divide by a fraction, I'm actually multiplying by the reciprocal. So this is now going to become 4 pi squared times m times r times f squared. Okay. So again, if you have to think about this one, it becomes 4 pi squared times m times r divided by 1 over f squared. So then you're going to multiply by the reciprocal, right? 4 pi squared times m times r. And then that's how you get that answer there. So this is another derived equation that we can use, 4 pi squared times m times r times the frequency squared, just in case they give us a frequency and they want us to use it in our formula. Okay, and then you can also remember too, on our data sheet, we do have AC equals 4 pi squared r over t. So that does exist. So you could skip that circular speed. Okay, so let's try a problem, and then this is our last problem for 5.2, and then you can have the rest of the period to work on whatever questions you'd like to work on. Okay, the compressor blades of a jet engine have a diameter of 42 centimeters, and they turn at 15,960 RPM. Determine the magnitude of the centripetal acceleration at the tip of each compressor blade. Okay, so let's take a look. What do we know? Diameter, 42.0 centimeters. We also know the RPM. Well, let's take our diameter and turn it to a radius because we know we're going to need that anyways. So let's go 42 divided by 2, and that's going to give us 21. And then remember, this is centimeters, so we're going to multiply or divide by 100 to get it into meters, and that's going to give us 0.21 meters as our radius. Okay, and then we also know our RPMs, which will be 15,960 RPMs. So remember, an RPM is a cycle per minute. So if we go back way to the beginning, I think it was this, yeah, it was this set of notes here. If we want to go from RPMs to frequency, we're just going to divide by 60. So that's going to give us, sorry, our, so those are our RPMs. So now if I want my frequency, I'm going to take 15,960 cycles. That should be minutes per minute. I'm going to divide by 60, and that is going to give me 266 hertz. Okay, and we want to solve for centripetal acceleration. That's our question. So we can start off right away and say that centripetal acceleration is 4 pi squared times r over t squared. And I know that t is equal to 1 over f. So now I can plug this into here. So it's just a bit of a shortcut. 4 pi squared times r over 1 over f squared. So now that's going to become 4 pi squared times r times f squared. So here we go. We can now plug that in. So AC is going to equal 4 pi squared times r, 0.21, times f, 266, and we're going to square that. Plug that into your calculator and you will get 586,600 meters per second squared. We are going to round to 3 digits, so now we're going to get 5.87 times 10 to the 5, 1, 2, 3, 4, 5, yeah, meters per second squared. Okay, so these videos will be posted on D2L, so if you want to go through them a little bit slower, you definitely can. You guys are now going to finish off the practice problems, so this is going to be page 267, numbers 1